All right, so I think we're finally ready here. Sorry for the little delay. The theme of today is glass, observations of glass. So remember what your sample looked like when you left it. It was a gritty powder that was colored likely with a certain metal oxide or composition, more than one. So those have now been heating overnight. Bless you. So you'll feel some radiant heat here. They're glowing quite hot at about 1200 Celsius. So can you feel that? Right? So exciting. The material has completely changed. It's no longer a powder. The sodium flux starts the process off and it begins to melt. And it kind of starts the process of dissolving and reacting like simultaneously. It's an interesting process. Meanwhile, carbon dioxide bubbles off because CaCO3 gives off a CO2 gas and becomes CaCO, calcium oxide. All the while it melts, and then those bubbles that are formed actually sort of helps stir and almost kind of knead the glass as those are expanding early on in the process. And so I do it slowly. I used to just kind of heat it up too aggressively, and it would kind of like make these bubbles that would pop over the top and then run down the outside and smear glass all over the inside of the furnace. It looks like the slow heat all day yesterday. I ramped up from 500, 850, 950, 1000, 1075, and all that was about a 12-hour ramp. And that way we're giving off that gas slowly so we don't have any of those volcanic eruptions. So I'm learning. It's only taken a decade. So it looked clean, and Tuesday was clean as well. So I'm going to go through a little bit more of the background. We're going to talk about some of the questions in the lab. I just bumped up our temperature to 1200 to give that just a little bit easier viscosity so that as I'm in and out of the furnace, we're going to be bleeding heat up and down, probably between about 1150 and 1200. It's a lot going on, so I will probably need 5 volunteers eventually to kind of help out with some of the tasks. We'll describe that, but if you want to get up close and personal with the process and take direct part, I've got jobs for you. If you just kind of want to make careful observations, obviously don't feel any obligation. I do record the process so that you can look back and see and compare viscosity and behavior during that pouring process. So if you wonder why the camera's here, it's number one, so I can track the furnace if there were no errors overnight. I don't know, it's kind of hard to wake up in the middle of the night and I'm thinking, I wonder how my furnace is doing. Well, now I can check, to make sure that the temperature's right. But then that feed is like 18 hours, and YouTube doesn't like large feeds like that. It only archives like the last bit, so I have to restart it so we can capture this as a savable video. That's why I had to mess around with that. So that's a lot of the logistics of what's going on today. So let's dig in a bit here. We already explained quite a bit about the background chemistry last week and how it's really just leveraging that polar covalent bond in silica. And so since all that was described, let's just remind you quickly that I did take some pictures of glass compositions right before we started heating them up. So just in case you forgot, that's the compositions from this lab. You can probably pick out yours there. It will look quite different. So that got loaded in the furnace. And because it's kind of hard to read hot crucibles, I put together a firing diagram so I know the sequence and where they're at in the furnace. So as far as what to observe and prepare for the lab, which we do next week, do, keep in mind there is a lab due this evening, right? That's lab 2. So make sure you get that in. This goes through some of the background we talked about last week, but we did not get into this part. All glass materials have what's called a viscoelastic range. This is a very low viscoelastic range. Notice how that is softening, and we're down around 5. This is probably for a leaded glass. Those would pour like almost water, not quite water, close to water at this temperature. Way too low viscosity. So viscosity is thickness. Low viscosity, like water, pours easily. High viscosity, like tar, pours in a very viscous way. It's measured in a unit called poise, one of several. So as a function of temperature, the glass thins down and flows easier the higher the temperature. Well, what we're doing is pouring all of these different glass compositions at the same temperature, nominally 1150, 1175, 1200, somewhere kind of average in that midpoint. So you kind of view it as if it's a high flux glass, we would expect that to have a lower viscoelastic viscous range, and it would curve in at our pouring temperature and produce a lower viscosity because its chemical composition defines where this curve resides on the temperature curve. Let's say we had a high silica low flux. That doesn't have as easy of a time melting, and so that would shift the curve this way. So when we're making our viscosity observations, keep in mind that we're defining a temperature and then looking at the intersection point of where that temperature intersects these various curves based on the individual elemental composition of your particular glass. And so then we can benchmark whatever, HI, J, K, L, M, all of our different glasses on whether or not they're above average, below average, etc. We're not doing this quantitatively, we're doing this qualitatively. And so the features that we can observe start off right off the bat when we start pouring it. I invert the crucible. How long does it take for that blob to start to flow out of the crucible? After that, once it starts to deposit on the steel, how thick is that string of glass? Is it lower viscosity, so as it's pouring out, it kind of pinches into a thinner bead, or is it larger? Sometimes that's kind of subtle. After the pour, you can discern the viscosity based on the size of the disc and the disc thickness. We're mainly going to focus on the size of the disc. And so if it was a low viscosity glass, it kind of hits and spreads out, and you will have a larger disc. So we'll measure sort of a caliper length for the diameter and benchmark those in our lab report versus a low flux, higher silica glass, which may have a smaller disc, and it would also be thicker. And of course, embedded in that is also less recovery from the crucible because you have a more viscous medium. But those are all sort of meta effects of viscosity that we can make an assessment of how the different batches compare. Does this make sense? So visual assessment of viscosity. This page will help with some of the questions. I used to have more standardized glass compositions, but that's kind of starts not being as fun as trying something different every time. And so if you see a reference to, is your glass more or less viscous than composition A? Composition A used to be our bland, run-of-the-mill control, and I should probably still do a control, but I took pictures of it instead. So essentially you can view A as maybe the average of our group. It's not critical that we compare it to these in the past, but this explains some of the trends. So this would be our average glass batch historically. With this one, it's almost the same, but we cut back on the amount of flux, and you can see the difference. Less flux, a more viscous glass, didn't spread out as much. somewhat subtle, but definitely an effect. So that's the effect of simple concentration of the flux. We also used to do a variety of fluxes, but bad stuff kind of started happening. So lithium, sodium, potassium, all three can be useful for fluxes. You see it's right there on the table, right on the first row, lithium, sodium, potassium. Sodium, certainly at this temperature, is the best behaved. Lithium, because it's a +1 but really small, is a more potent flux. It does a better job of disrupting the bonds it is interacting with in the silica, and as a result, it makes a very low viscosity, easy to pour glass. It also frequently shatters. I put that one back together. But you get a lot of recovery from lithium. Another issue with lithium is that it's so small. You know, if you look at that 6.9 grams per mole, it actually starts to evaporate, and it fluxed the inside walls of my furnace and made them weaker. And so I haven't been putting lithium flux in the newer furnace as a result, because lithium is just kind of destructive at this temperature. But that's there for you to answer the questions. And if I shifted my temperature range lower, I could make lithium glass more manageable. Sodium, that's run-of-the-mill soda lime glass. That's what we're mainly focusing on. Potassium also works, but because that's the opposite, it's a fatter, bigger, distributed +1 charge. At this temperature, it's not quite active enough to be really effective at fluxing. And so those glasses are often really tight, really viscous, and they almost always shatter about a half hour after they're poured. Almost always. But these you can use to get your trending to answer the question of what would happen if we changed away from sodium flux. But all of ours were fluxed with sodium this semester, just because they're more stable. Make sense? So use the pictures, use the data there to answer the specific questions. The questions might imply that we made these in lab. Just use the pictures. And so we prep the batches, and we're about ready to pour them. So you'll have some wrap-up questions about some of the chemistry, about trends you observe, whether or not it shatters. We had a good record on Tuesday. None of them broke. None of them shattered. We'll see if we can keep that going. It's rare to have a year where nothing ever shatters. So I hate to break it to you, but you guys probably are the winners. We'll see. Or maybe we'll be the first. But we put some physical observations as well as color observations. So the color observations, you can use the spreadsheet, assuming it's still here. So this spreadsheet will be your friend for calculating percent metal composition. So let's say H, first one we're going to pour. It was higher silica, should be higher viscosity as a result. Lower on the low end of flux. So I'm expecting that to be a fairly sluggish, thicker glass. So that's what the viscosity is doing. What's the color doing? Well, we added 0.25 copper. So that's on the low end of copper. So that's light blue. With a 0.05 manganese, middle purple. So bluish purple. Well, what's the composition of the metal ion in that batch after it off-gasses carbon dioxide? You see it loses about 30 grams of mass from off-gassing. Well, that's where this table comes in. So this is our predicted post-fired batch, and our weight percent copper, 0.15%, and 0.02% manganese. Those are positive, can't really tell, plus ions. So this is your friend. This will help you out with your assessments. So you can populate that table in your worksheet just to think about that relationship between metal color and metal concentration and depth of color. Those are the observations we're chasing here. Yeah, where you go? ending questions, and then it eventually turns into these more conceptual couple videos to watch. That's Smarter Every Day. Pretty good. Video explaining some of the highest internal stress field glasses you can make. A water quenched glass called a Prince Rupert's drop. It's a weird name, but you can shoot them with a whatever handgun or rifle, and the bullets just splatter on the surface. It doesn't break the glass. Yet there's these tails that if you just nip the tail with a pair of like wire cutters, the whole thing just explodes. They're crazy. So to kind of take a nod from that, we are going to do internal stress analysis using cross polarizers. Is this a familiar story with any of you? Polarized light allows you to see things you wouldn't otherwise be able to see. So these films only allow, or preferentially allow, vertical, let's say, polarized light to go through. Most of the time light is in random polarization directions. And so if I put another film parallel with that, there's not much change. However, if I turn this 90 degrees, notice I can turn the light on and off. You can see that, right? My face. I'm going to make my face disappear. That's a dream come true, Dr. Ray, right? So I can control that. So that's because I've got these plain polarized light filters. But now, a stressed piece of glass has its own ability to polarize light. So if I take one of those and I put it, that one's in the eye. Bad example. There we go. Take one of these and put it through. Maybe you can see that, maybe not, but there's these bands of color that will be a lot more obvious on the light table. But once these get cool enough that they're not going to scald you, you can then do an internal stress analysis, again, qualitatively. But you're looking for areas where the color banding stacks up on itself. That's where the highest stress field is, where you have tight bands of rainbow color. When those stretch out like they do in the middle and you have more of these zones, that's a lower stress. But you'll be able to see that there is internal spring pressure pulling toward the center of the glass against this outer edge that cooled first. The middle cooled last. So as a result, it left this fingerprint of stressed bonds that we can see with polarized light, which I think is awesome. Hopefully you will too. But that allows you to analyze more than just meets the eye with your glass. And Dustin off of Smarter Every Day goes into a lot more detail on that. Does this make sense? Glass. All right, so the way the workflow will proceed is I'll get some helpers now, and I'll explain the jobs. And I did PDF your batch records, so we'll flip through those as we go here. But once we're done, you can pick those back up. But we're going to pour the glass. That'll take about a half hour. It then takes about a half hour plus to cool. So during that time, we will look at two different approaches to glass. The artistic approach. We're going to look at Dale Chihuly retro video. I still like it. And then glass bottle formation, utilizing this material. I'll then explain directions and instructions for cardinal glass. I'll have you sign the safety waiver that says, it's kind of a liability waiver, and you're disclosing that you are not going to go give their secrets to their competitors. So that'll pass around there as well, and then hopefully we'll be close to being cool enough to pour or to observe glass. So, jobs. I'll quickly explain the jobs, and then we'll ask for volunteers. So, the jobs are door, torch, stamp, call it MC, somebody just keep me straight on which one we're pulling from the furnace, and fire individual that just stands by this just in case me or something else catches on fire. So door, pretty straightforward. So I'll need somebody that probably has on maybe a welding glove or two, and your job is to slow up and then stop, and don't let it bang because there's brick on the inside, you don't want that to come out. And then as I pivot around after grabbing a crucible, you just move back in and carefully seat that. So that's the door. I'll then be operating in this space, and I'll be pouring 11 compositions of glass here. Because that's going to start cooling down, I don't want to string it into fiberglass, so I'll need somebody to do the torch work. So for this, you are basically heating the bead of glass as it's pouring out of the crucible to keep that the hottest part. So then, when it's time for me to lift this now cooling off glass and separate the crucible, it's not going to like string along, and if we didn't do that, I would be trying to lift the glass and it would just still be attached to that cooling glass. And so this works beautifully. And then that little defect, like the top of a chocolate chip, then kind of pulls in and smooths off into a nice little disc. And so if your torch work excites you, I've got a job for you. So then, because I've got way too many glass batches that have accumulated over the years, we put catalog numbers on them. I am going to anneal these, which makes them safe enough that you could take them with you if you desire, but obviously you don't have to. Custom paperweight, great Christmas gift for mom. So I'll need somebody to stamp. So with stamping, we've got these dies that were letter plus 4 is our sequence this semester. So H4. Now, when you're looking at this, if this happens to be your job, it's going to look backward. It's going to look like backwards 4H. And so I often just kind of press that against the skin to make sure, don't press too hard, but just to make sure it's oriented right. And so once you get those lined up, after the torching is done, you just sort of move in and just press that into the glass. And it can get a little bit toasty, so some people wear a nitrile glove, and that just keeps the radiant heat down. You could wear a welding glove, but it's really hard to hold these in the right orientation with that. But the rubber glove, nitrile gloves work, and not everybody wants to do that, but it can actually be pretty toasty. So, but that's another one that gets you up close and personal to feel the heat. This individual just kind of keeps me in line. It's hard to do, but just helps me work through the diagram just to keep it straight. And then finally, I think I've probably already gone off on fire extinguishers before, but just in case you didn't hear it the first time, we don't give fire extinguisher training. We just want people to safely and calmly exit the building, right? Well, here it is, fire extinguisher training. I'm not going to dispense this, but P, pull the pin. A, aim at the base of the flame. Not the flame itself, the base of the flame. Squeeze. And sweep side to side. Pull, aim, squeeze, and there you go. Fire extinguisher training, you are now experts. But never had to use it, but it's not out of the question that something odd will eventually happen, and so you don't have to I had a guy once that was like, yeah, I'll be the fire guy. And so the moment I opened the door, he went like this. I'm like, it's unlikely I'm going to catch on, but I appreciate the enthusiasm. You don't even have to hold it. I mean, just in case, It's like he is ready to hose me down. So, volunteers. Anybody want to do the door? The door. Any takers? All right, thank you. Anybody want to do the torch? Torch, okay. I saw that hand first. Anybody interested in the stamp? Stamp? So I guess you were first, so I'll have you do the stamp. Then Somebody to help me with the firing diagram. Thank you. And then finally, backup fire option there. Anybody want to be there? Anybody got fire safety training? All right, appreciate that. Okay, so we do need to wear our at least safety glasses, but definitely have to have your eyes covered because when these things shatter, here's what they look like. I will pour it. About 20 minutes later, we'll hear this, and it doesn't like go off like a grenade. It just shatters outward, and it just kind of like hits you with glass chips. So it is an eye hazard. So definitely have eye protection on. And when you're handling these today, keep your eye protection on. Ideally, next week or the next time we see these, which I guess is in 2 weeks, I'm going to take all of our glass and load them into this furnace, and I'm going to heat them up to about 550 Celsius. 1200, 550. That's above what's called the strain point. But it doesn't melt. It just gives them enough thermal energy that these bonds that cool and are like, I can't take it anymore, and that internal stress, it gives them enough energy to break that bond and bond with something closer, and then something that was stretched over here breaks and bonds with that original site. It relaxes the glass and allows that internal spring pressure that is why it shatters. I mean, it's weird. There's videos on the channel that have been captured that this glass is just sitting there for 20 minutes motionless, and then all of a sudden, where's the energy come from? Well, it comes from trillions upon trillions of bonds that are stretched like a spring, and something finally breaks that tension, and the whole thing shatters and releases that internal spring pressure. And so it's potential energy stored in those stretched bonds, and it just sometimes releases because we are quenching the glass. So I could talk all day, but I'll stop. So I have to wear this shiny suit, which will make me not catch on fire. Feel free to get your places and get familiar with the torch and all that. The torch you have to pull a little slower than you expect because it's electro actuated, and it's kind of like you got to flow the gas before you hit the igniter. Yeah. Torch usually you don't have to, but it's up to you. Some people eventually put on a welding glove, or the heat leader in the second half does get kind of a lot of radiant heat. Another thing with the torch is torch angle matters. And so to begin with, you're usually torching at this end. Then the next one, you're trying not to let the flame wash go over the previous one because then you get uneven heating. So you start angling, so 1, 2, 3, and then 4, you're vectoring away from this row because what I've seen is that if you're this way, this one blows up. So this way, and then you're sort of angling away, and so that does put your hand above cooling, and I'll also have crucibles here, but we'll manage all that. Just let me know. But you may want eventually a glove. It's kind of a secret. And with the door, you can still get the feel for it. It's a slow up, and then don't let it bang at the top. It's a slow top, and then slow back down because there is hot brick on the inside. It's kind of brittle. So, and just kind of keep the distance so that radiant heat doesn't get you. So. All right, we're almost ready. This allows the video to have a little clearer description for those that want to look back at the glass compositions. So, all right, we should be in pretty good shape. So, I'd say probably standing right here would be the best spot for you. So notice we're going left, right, mid, back, and then that's the way we're going to unravel this guy. So H is, as we already assessed, a higher silica, lower flux with a copper manganese purpley blue is what's predicted. It does have sodium sulfate, so I've had hit and miss results with that. It's supposed to make fewer residual bubbles. We'll see if that pans out. So H4. So and it's probably standing back here is probably better because I pivot around the front with the hot crucible eventually. And so we'll mostly just row in about 9 or 12 depending on how I economize space. And we may put the final ones here. We'll have to wait and see. So, you guys all ready? All right, so pulling formula from the left. You gotta pull again.
Like.
It might, yeah, so unclick.
Okay.
Nope, you gotta restrike. You can probably just take the glove off. There you go. So, there we go.
There we go.
All right, look closer, right about there. And so now, look closer to the disc as well. Down, there we go. And now try to concentrate that fire up on top so that it will pull that defect down into the surface. So go down there, and then fire polish. There we go. So just kind of wash over that, try to get that to pull down in. It's getting there. Maybe up just a little bit. Yeah, there you go. Okay, that's probably about right. So you can move in and stain. Yep, in the orange. Usually kind of around the edge, but that's fine. Well, this one had a little bit of a different timing because of the torch, but that makes sense now. So now
Okay.
practice the pull a little bit, so it's a slow pull, so it's gas, then click, and ignites. Nope, and it's locking.
Okay.
There's a button that makes it lock. Don't push that.
Okay.
that silver that
That's
one on
the one.
top. That's what made it
Okay.
lock in on.
Okay.
So yeah, that one, just single pull.
So just-
I should have given you more explanation.
Okay. Okay.
It's like, as you're pulling it, it's like gas, click, ignite.
Okay.
Don't pull all at once. Slow pull. There we go.
Ah,
Yeah.
okay.
Like that. So, okay. And avoid the temptation to pick up fiberglass because it's kind of deceiving. It will feel flexible, and then all of a sudden it shatters and sticks into you like a hypodermic needle. And so this is thicker than fiberglass insulation, so that makes it actually kind of dangerous. So that's kind of an interesting color. It is a bluish purple with some metal fleck, and so the carbon monoxide from the flame reduced a copper surface film, and so we have this like coppery edging on that glass. So, all right. So next up is I. So I4, we've got fairly straight 90, 50, 25. So we're expecting kind of average viscosity. And we are at 3.7 grams of iron oxide. So that typically is greenish in color. So yeah, we'll focus right here, and you can point that one out if you want. Or kind of like that.
Okay, that
So
makes
it's
sense.
kind of that. All right. Okay, going for I from the right. just kind of the lower edge, not quite in the middle, just kind of. So I just realized I just re-aimed my camera. So the way to do these looks a little more like this. So if you imagine this is the disc, it's usually like, I should have demoed this a little bit more. It's more like that. So it'd be kind of like bottom centered. That's a little more stable. I think we're still fine, but that's probably the more ideal spot, like just about like that. All right. Goes too far out of order. Let me re-aim the camera here. Let's point the right way. All right, that's about perfect. All right, so next up we've got J4. J4 is 80, 50, 25, so nice average viscosity would be predicted from that. And this one is just manganese, 0.25. So we're expecting purple. So we will try to get this one positioned so it doesn't run into this one and doesn't hit the edge. You're also going to hear some interesting chorus of sounds. That's called crazing. It's caused by the fact that the glass shrinks at a different rate than the crucible. And so as that glass solidifies, it then relieves that stress like we've been talking about by cracking because it's got this differential tension on the crucible cooling at a different rate than the glass. So eventually we'll be hearing that a lot. That's normal. And also keep an eye on the color and how it changes. As this cools down, the metals are settling into a slightly different geometry as it cools. And so it's not unusual to see it go from brown to green or change at least in some degree. Like this is, I don't think we've seen the last final color. Well, actually maybe not. There is something a little different about that. Normally iron is more green. This one looks like it did tilt towards that kind of a brownish color. That might be the final color. We'll see. All right, so manganese is next. J4. One from the middle, right? Okay. Just hit that, get the pull down in as much as you can. Almost there. Okay, I think that looks good. There we go, perfect. All right. So yeah, you can tell from that strand there, that is going to be a nice purple, almost like an amethyst color. Okay. And once we're done with all this, I'll break off that strand of glass, and then they're more stable. You can look at them. I think I see what's going on here. This iron was made with mason sand, and mason sand is like, it has a bunch of who knows what in it because it's that brownish, blackish sand. So that's why it's like there's other stuff in here that I really don't know what the color is from because it was an impure sand. Keeps it exciting. So, and is the heat all right for you? Short sleeves doing all right? Yeah, that's a nice purple.
Start doing.
Yeah. So right there, just watch your sleeves. This, you'll be kind of at an up angle, but tilting over. Yeah, not like that.
But
Yeah, it's a, you got a dangerous job, electrical coordinator. Okay, so next up we have K4. So that's 85, 55, 25. So that's a lower silica, higher flux. So we're expecting this one to be a flatter pancake. By a little bit, lower viscosity. And we've got 3.5 iron oxide. Now, interestingly, K, let's see what sand or silica was used. Also, mason sand. Okay. So that means it probably would be similar in color to this. We'll wait and see. So probably pull all the way up to here if we can. Okay, going from the left. All right. Man, look at that. That poured out really quick. That is a flat pancake there. That looks good. Nice and flat. Alrighty. Color does look pretty similar on the strand, so I think we're headed in the direction of that. Although it has darkened up a bit. So probably still in that yellow-brown spectrum of sorts.
so then for this next.
So you can stay in the same place, but you'll just be now angling so that yeah, I mean, and it's okay if a little bit of fire gets on this one, but I would try the previous row. But just kind of try to keep it kind of that way. That's it. Okay. Just be careful. So now we're in L. L 90, 50, 322. So a subtle. Okay, so we bias towards sodium flux on this one. So, well, I'm not sure exactly how to predict that one. I think it would be less viscosity than average, but not as flat as that last guy, probably. So on that one, we also got 0.12 manganese. So this probably a lighter purple. We predict. Ooh. Yeah. All right, so L, we're pulling from the left.
Right.
Right. Okay, let's go. Yeah. It does look a little different for some reason. I'm not sure why. Yeah, so it's interesting to see sometimes with that unknown impurity how that interplays with the predicted color. So yeah, some of these I guess we'll have to wait and see what the final color even is. So all right, questions so far? Hot work here. So next up we've got M4 in the middle. And it is 95, 45, 24. So higher silica, lower flux, probably a bit thicker glass. And we've got chrome iron on mason sink. Take bets. I'm thinking greenish, but I don't really know. So go for right there. Did you get enough clearance? Okay. So one from the middle. Good.
Where's the bunch of pictures?
Definitely thicker. I'll try to concentrate some heat on with some chunks in there and bubbles. Let me back off a little bit with the tips of the inner blue are the hottest part. I don't think we're going to move it too much more. Okay. So that one has bubbles. That could be a bad sign.
That stamped very well. It didn't want to press.
It's there. It's there. I think we'll be okay. But that one we're going to have to keep our eye on.
That's gonna explode.
Well, sometimes those internal bubbles are weak points, and as it starts tightening up, those bubbles end up being a weakest link in the chain. So I don't know. I've seen those go both ways. So, but that is the one on my radar now that you have to keep. The good news is we have 20 minutes at least. Maybe 15. So, question is, can I get 2 more rows there? I don't know. I think I'll probably have to move back there, so we won't push it. All right. Next up, we've got N4. And N4 80. That's really low. 80, 56, 28. This is going to flatten out like crazy. Which would be interesting. So low viscosity glass, and then a chrome copper. So well, that's high copper and low chrome. So it's going to be like a bright blue, pull back green a little bit. Greenish bright blue, really flat. That's my prediction, based on science. All right, point from the left, in 4, in 4. We're in for it. Keep warm. Not quite as big as the one beside it, maybe. Greenish blue. A little strand there. We'll see if that. See how that pans out. Go. Yeah. Anytime you get copper in the mix, you can get that metallic reduction in the top layer, and it's kind of a cool effect. You'll see some of the example batches I've got that are higher copper, and we've really tried to focus on doing that, and we've got a few that are almost fully covered in copper on top. These are more subtle because we're not really trying to, it just kind of happens naturally. But yeah, interesting effect there. All right, next up, 04. So 04, 88, 50, 25, pretty typical mid viscosity with iron and manganese. Greenish purple? Is that brown? I don't think greenish purple is a color. I think that's brown. So, brown? Alright, so we're kind of angling this way. You got a little more real estate in the crucibles, but there'll be more latent heat than your global. Yeah. And you're doing alright not singeing yourself?
Not too bad.
Not too bad. It can get pretty hot. 1200 degrees. That'll get you. From the right, go forward. Okay, so brownish maybe. This has gone to mostly green now. The previous one. And that looks like Mason sand again. It's so hard to predict that. Oh, that was you guys. Okay.
I'm
Nice.
hoping for brown with like purple flecks.
Oh. Okay, so then you were kind of thinking the same thing then. Interesting. It doesn't really fleck very well because it melts out and mixes in pretty efficiently. So I think you're probably just going to end up with perhaps a brown spectrum somewhere. But, so put the next one here, and then the other two maybe just right on back, or maybe I'll avoid the rough spot. So that's where we're headed. I think we've got 4 more. 3 more. Okay. So composition P 100 390.25. Higher silica. So this will be more viscous. Manganese. So manganese is color of the day, I think. Lots of different takes on purple. So in this one's also 100 grams of Fisher pure silica. This one's going to be small because Mason sand, because it's impure, melts easier than pure silica. The more impure it is, the easier it melts. So this is going to be like a double whammy: high and pure amount of silica, but it will give us a nice clean purple, I think. So we'll see how that pans out. All right, P4 in the middle. P for purple, yeah. Good point. Precisely. Come on. Come on. This one might blow up. You gotta keep your eye on the little ones. They're the ones that get you. Maybe we'll be alright. Just try your best to get that to pull in a little bit. If we can. Okay, okay. Yeah, I think that's probably pretty good. I don't know about that one. It could be alright. It's following the theory though. I mean, light purple, high pure silica. Yeah, that's about what to expect. We got a nice purple strain developing there. So science. Am I ruining the suspense, or do you want to know what each one? What I like to, the reason I want to do that is to kind of demonstrate what's the trend, what would we expect, are we going to get it or not? It's not always the case. I'm still surprised every year with some of them. So, wow, that's really flashing purple now. So, two more. We'll just kind of plop them right there, I think. Yeah, and you just angle it away so you're not hitting these, and you'll be good to go. Hopefully, we'll get out of here before these create any problems. So, maybe. Let me adjust the camera. Hoover a little bit. Yeah, it's just like, it's almost like it's serendipitously sorted. You've got blue, yellow, purple, well, green, blue, brown. Variable.
Yeah.
So, small blade in fire. It's not you, it's not me. Okay. Anybody else smell that?
Yeah.
What just happened? Did I touch
Get the
the...
fire extinguisher.
No, no. I think I might have touched the surface of this. Let me know if I'm on fire. Q4. Q4 is 8950 with dolomite. All right, first time we've seen dolomite. So 1311. That's a mixed magnesium, calcium carbonate, fresh mineral, sweet. So straight run with a substitute for dolomite, calcium carbonate, and chrome copper. Green blue again, green blue. So, okay. Q4. Yep. A little closer. There we go.
Interesting to see what happens because we used the Lake Michigan sample.
Oh, you did? Okay.
You want to take pictures?
Yeah, so far we're a lightish green, but chrome develops darker green as time goes on. So we'll see how that might deepen a little bit.
That's a good sign.
Maybe it's this coating on this pad. Put it fairly hot crucible on that. These are supposed to be. What's that?
Smelt it when you poured in the last one too.
Okay.
It's just being gloves guarding.
Well, the last few pulls that I get, my gloves will be smoking a bit. I don't know if you're seeing that. And I've kind of worn. I'm starting to wear through a little bit. So, all right. Last but not least, R4. We got 85, 50, 28. A little bit low. No, a little bit. Yeah, a little bit low on silica, which means it should be a little low on viscosity, a little more flux. With cobalt. All right. So a nice cobalt blue. I don't think we had any pure cobalt blue last time, so this one should be a nice example of cobalt blue, dark blue. And it was Fisher silica too. So that's going to be a pure cobalt blue, maybe a little bit small. Probably all the way over there will be our target.
Yeah.
Except summer. we're kind of stringing down in that one laid out a little bit too far. Okay. I'm seeing a lot of color on it. This one did get the color, right?
Yeah.
There you go. Okay. Okay, I'm seeing the blue now. To begin with, I'm like, I don't see the blue. It's turning blue. Just a little bit. Hint of blue. That's kind of seawater. That's kind of cool. And nothing shattered yet. Okay. I retract that statement. All right. It's not over till it's over. Yeah, now we've got a nice blue developing. Cobalt blue is one of the most potent colorants. And so it often is so dark you have to really get some light on it to see it. So by backing off so far on that blue, you're getting like a light cobalt blue, and that's hard to do. So that's kind of cool. Yeah, that's nice. All right, so that's the hot part. So thank you for your efforts in hazarding yourself. I do appreciate it. We'll take that and get out of the hot zone. Ooh, we're almost out. So just enough. And so now we'll watch a couple different takes on what can be done with this. The first one is, like I said, kind of retro. Glass artist Dale Chihuly. He's a yeah. Feel free to go up and snap a picture if you want, just in case they shatter later. Don't touch it. It's still pretty hot. Make sure you have your goggles, your glasses on. Get your eyes protected.
What?
That's something that,
Oh, that's a better, closer one. Oh my god, it looks so cool.
at least in terms of color, we all.
Oh, no, like the line. Nice.
Oh yeah.
Already see the stress. We don't even need the paint on the top.
Dale Chihuly's studio in Oak in Seattle, Washington. This is where Dale's book is made, and where we conduct. Okay, we're at the Boathouse, Dale Chihuly's studio in Oak in Seattle, Washington. This is where Dale's work is made, and where we conduct most of the business that he does. This is the hot shop where we have hot glass.
We first met Joe, who was telling us a little bit about why Seattle is so good for glass blowing, and it's because its climate is not too hot, not too cold.
Our glass is 2,150 degrees Fahrenheit, and that's the working temperature of the glass. In order to melt it, we put it on what's called high fire, and it goes up to 2,500 degrees to melt it. So we should take a trip to the furnace.
Okay.
That's
That's a statement I never really expected to hear.
oh no,
We're gonna take a trip to the furnace.
trip to the furnace.
So what are you doing now?
Well, I'm gonna gather this, what we call a little gather here, and the pipe kind of heats up as we stick it in the furnace there. Wow. So we have this little device to keep ourselves from burning ourselves on the pipe. Turn, and then you kind of let it fall on center. There you go. It cools off.
Yeah.
There you go. See? Natural, that's the right. Hang it down and it'll go down.
Is the burn unit nearby?
We have a little device over there that patches us into the fire department. Kind of come out,
Yeah.
and then you lift it on out of there. Okay, up and out.
Yeah, there you go. Keep turning. Wow. Good. Keep turning. Good. Right now.
There you go. There you go. Now this is the marver. This is what we call the marver, and now you are marvering. Marvering the glass.
Marver is just heavy metal.
Yep. Very good. Oh, and this is a good shot coming up here too. This is what we call a roller wrap.
We'll return to Foster in just a second.
Oh, they're applying the red to it? Right.
Yeah. And these rollers are offset, so the bubble moves down and the color goes on.
It's like taffy.
Hale founded it.
Oh, he did?
Yeah. He was the founder of the school.
So is he like the main glass man in Seattle?
He's about the main glass man in the world.
Really?
Yeah.
I was going to school here at the University of Washington and was taking a degree in interior architecture. Started getting interested in glass, started melting glass, and one night I blew glass out of a little kiln. And then from there I decided I wanted to be a glass blower.
What we're working on today are these wall pieces, okay? And so what you see a dark bubble on the inside?
Yeah.
That's actually an air bubble with a thin layer of color that's been it. Right there is about to drop on to the pipe. We're going to just reheat it, shape it, and with my great team, we'll hopefully get it in the box.
So,
Okay,
stay out of your way. Where should we be?
no, I don't want you to stay out of it. I want you to get right in my. I'm gonna have you help me a little bit here.
Martin works for me, but he also works on his own work and has his own exhibitions. And many of the glass blowers that have worked with me have gone on to develop their own careers. Some of them, like Martin's, stay around and still work for me. Others go out on their own entirely. But there are some, I don't know if anybody told you, but there's something like 50 glass shops now, glass furnace studios in the Seattle area.
It's not really glass blowing, it's more like glass shaping. Because there's a lot of prep work into shaping the bubble and very little blowing.
Well, glass blowing is difficult to get started in because you have to have the equipment.
A little further.
So you've got an initial outlay of, a couple $100,000 just to have a small glass shop, and then to run it costs a couple $1,000 a day.
Actually, what you're gonna do is, these are wooden paddles and they're to protect me from the heat.
Okay.
All right?
Teamwork. Hey.
You guys are awesome.
Oh wow, I can't believe you can even talk.
Turn. Cap. Oh my gosh.
Should I be up there for you?
Wow. Blow? Yeah, shoot my chin. Stop blowing. All right, good. Level. Tip up. Right here. Don't stop on it.
This climate is conducive to glass blowing because it's not too hot. The only really bad climate for a glass blower is a hot one.
When you blow glass, you blow the bottom of the vessel first. And now we're going to break it off the blowpipe. Okay, pull. Glass always breaks at the coldest spot, right? So it's a little drop of water here, drop of water there.
Yes.
Boom.
Wow, there it is.
Is that cool?
What you saw down there was those techniques have been used for 2,000 years.
Please make it as you get in.
Any guesses on what the color it was for that particular piece? See the color? Keep an eye on it, see if you can figure it out.
Good. Now push down. Okay. Good. Hit the lip pad with one paddle. Good, man. You are on the ball.
I'm just pushing down.
Push
I
harder.
can't even see
Push
it.
harder now. Ease into it. Push harder. Push. Let them open up. Good. Push. All right. Now, when it starts to feel like it's not moving anymore, you're done. We've got as much work on that heat as we could. Now, come out. Good job.
Whoa. These
And
were
they
on
say-
fire. And so went
Pull heat, Carl. All right. I'll take those.
Okay. So what's that?
That was good. We got about 2 heats left.
Okay.
What we're doing now is we're going to peel this ball open flat to make the wall piece.
I can't recommend doing this.
All right, so is your coolers work?
Here, well, yeah, essentially their ovens are 900 degrees. The timing is just critical on that because you've got about, while it's heating, that all the work we're doing comes down to that very last heat. That's where the shape is made, that's where the beauty happens, that's where the nuance, the delicacy of the whole piece. All that work is just for that one heat. And then in a few seconds, you come over here, and if your timing's off, crash, it falls on the floor. Where do you get your inspiration from?
I'm lucky in that the ideas come to me. You know, I probably don't run out of ideas. You know, sometimes you wonder if you run out of good ideas. Glass is a lot like water. You know, there's a lot of, I like water, I like glass, I like ice. There's a lot of characteristics. And it also kind of works like the ocean, makes forms like the, you know, there's some connection between all of that. So I end up blowing glass and stuff, everything. Half the stuff I make looks like it comes out of the ocean, even if you don't want it to. I like the rain. It's really, I find it conducive to thinking, and I always tell people, gee, if you had to write a book, you know, you want to go to the Caribbean to write the book, or you want to go to Ireland, which is a lot rainier than Seattle. And where are they going to write the best book? Even most people admit it's going to probably be Ireland. Somebody is an aspiring glassblower, where do they want to go? They want to move to Seattle, because here we've got, you know, more glass activity than anywhere else. I mean, Venice has more glass factories and furnaces in Seattle, but we're second to Venice. And I think I would be proud to say that we probably have more glass artists.
Similar to what I was saying, that's their annealing oven. And notice he was at 2,500 down to 900 Fahrenheit. We're doing pretty similar heat sequence. We're up around 1150, 1200 Celsius, and our annealing process is going to be above the strain point at around 550 Celsius. So similar temperature regimes. Anybody figure out the color that we used for that one? It's purple. It's probably manganese. So that's likely manganese glass. Anybody ever been to a hot shop and seen glass blowers in action? Yeah? Where was that at?
Glass orchard outside of Eau Claire.
Oh, really?
Yeah, they have a glass blowing.
I didn't realize we have them that close. Cool. Glass orchard.
Yep, glass orchard.
Yeah, the
Apple
ones that
orchard and glass blowing.
I've seen were up in Corning, New York, where I happen to see. I've never seen his operation. I used to think that he probably injured himself with some crazy process, but no, that was actually a car accident that took his sight in that eye. But he and his wife have crazy successful career and are commissioned to make these art installments all over the world, really. But airports, museums often will hire, commission these glass works. So if I'll get to it here, just imagine making this out of glass. I mean, look at the color. It's crazy. I wish I knew his recipe for those. Those are crazy bright orange. Oranges and reds are really challenging to make. So he's got to be doing something. There's got to be some tricks. So I realized that this maybe artistic side may not quite feel like your wheelhouse if you're science, engineering, manufacturing, mechanical. But I think it's useful to think about what you can do with this medium. This one's going to feel obviously a little bit more applied, making bottles. The furnace that you see right at the beginning is actually remarkably similar to the furnace we're going to witness next week. But instead of making bottles, they're making window glass. 20 miles, 12 foot wide a day. That's a lot of windows. I still have a hard time. 20 miles? Crazy. So with this, instead of making it flat and floating it out on a bath of molten tin, they push it through these drop valves and pinch the glass to make these blobs that then shape by falling through dies and then get conveyed to Parison forms, which then get picked and put into a blow mold. And this machinery is timed perfectly. What I want you to think about from a manufacturing engineering standpoint is, what does a bad day at the glass bottle factory look like? You know, as these bottles start hitting at the wrong time and flying all over the place, horrifying. But it's right in, it tuned up on this one. But a lot of interesting things to see how they leverage this whole process around glass. So I'll probably get an advertisement, so I'm going to block that out real quick.
That are abundant. Making it glass is made of natural ingredients that are abundant. Making it uses less energy than producing metal or plastic, and it can be endlessly recycled. Whether they're coloured or clear then, glass bottles and jars are always green. The recipe for glass combines several natural raw materials. The main ones are silica sand, soda ash, and limestone. Silica sand usually makes up about 45% of the batch. The soda ash helps melt the silica evenly. It makes up about 15%. A limestone content of about 10% makes the finished glass more durable. These ingredients are combined with recycled glass called cullet. The factory's equipment feeds precise amounts of the materials into a furnace. After 24 hours at 1500 degrees Celsius, a gooey liquid that's the consistency of honey is produced. The molten glass pours out of the furnace. Shears cut the flow at precise intervals to produce cylindrical globs. Each glob is the exact amount required to make up one bottle or jar. They drop to a device called the scoop. The scoop moves them to troughs that feed them to jar-forming and bottle-forming machines. A glob of molten glass goes into a preliminary mold. Matter of seconds, it comes out as a miniature version of the bottle, known as a parison. Each parison then moves into a blow mold, the cavity of which is the shape of the final bottle. The equipment blows compressed air into the parison, stretching the glass outward towards the wall of the mold cavity. This process creates the final bottle shape and hollows out the inside. These are amber-coloured beer bottles. The colour is produced by adding small amounts of iron, sulphur and carbon to the glass mix. A similar manufacturing process is used to produce other types of bottles and jars. In this run, the company is making 375 millilitre wine bottles out of clear glass. This run is producing bottles also out of clear glass. This mold though has a special feature, a recessed insignia on one of the walls, which produces a raised insignia on the front of the bottle. After the bottles leave the forming machine, they travel through flames. Otherwise, they would cool down too quickly and crack from thermal shock. A loader now gently pushes the bottles into what's called an annealing layer. The bottles cool at a controlled rate as they move through the layer. This gradually releases the stress from the glass. As the bottles exit, they're sprayed with lubricant. This enables them to move smoothly through the rest of the inspection and packaging line. The bottles now single file to head into the automatic inspection station. As the machine spins each bottle, cameras and probes check for imperfections such as cracks or bubbles. The inspection equipment then examines the top to check dimensions and ensure the threads for the screw cap are molded correctly. Before shipping, each bottle gets a final visual inspection. The proportion of cullet in glass can be as high as 90%. Cullet melts at a lower temperature, so for every 10% of cullet in the mix, the factory uses up to 2.5% less energy to produce its glass. Now that is a clear incentive to recycle.
And so now you have heard the rest of the story for the industrial side of glass. So carrying on that theme, we can look at some intel. I always feel like I'm prepping people for a bombing run when I show this presentation, because I've got some satellite imagery telling you where your targets are going to be next week. So follow the red line here. So we are here, Stout campus. Get out here to 12, go past Culver's, you go past the hospital, then you go past, I guess some of you know what this is, it's a police station, and you turn on Stoke Parkway, or Stocky Parkway, you're going to pass a small airport, 3M, and you're going to cross over 94. This is Cardinal Glass up here. So as you are approaching, you are going to feel overwhelmed with excitement, and you are going to want to turn here on Badger Road, which will lead you to the loading dock, and you will not be able to get in. So restrain your enthusiasm. You go past, and you will turn here. Your visuals are a water tower and a smokestack. Go in between those. In between those. And you will park anywhere you feel like here. Just follow the one-way signs. And then you walk into this part of the building. And there'll be a reception area where they will usher you back to a conference room. We'll watch a video about Cardinal Glass. It's pretty well made too. Really just let you see their industry. And then they'll take us on the tour, and this takes us to the hot end. You see the furnace, the tin bath, the annealing leer, and eventually it's a long leer, the cutters, and then all the warehousing. And they have actually expanded on since this is probably, I've been doing this too long. This is 2011. This is old Intel, right? There's now this whole new wing back in there for storage. So that's where we will meet. The tour takes about 2 hours. So since we are usually meeting at 1:30, we'll meet at 2 o'clock, and it'll be basically 2 to 4 next Thursday. They do provide you with safety glasses and radios. You don't get to keep them, but radios because it's pretty noisy in some areas, and this way we can hear what's being said about the process. So we all have our rides figured out. Anybody still need a ride? If you do, don't be bashful. Let me know. Anybody have an extra seat in their car you're willing to take? Got one over here. So if you're still looking for a ride, we got 3 guys with extra seats. Be happy to, I'm sure, take you along. So feel free to touch base there if you're still searching. So I do need to pass around the approval form. So this is what you're signing. We'll walk through it. So I'll go ahead and start passing that around. So on the back, just sign it, print your name, date. That way they'll let us in. But what you're acknowledging is that this is a manufacturing facility, dangerous conditions. Yeah, they could exist. They're really excellent. I'm amazed how close they let us get to their process, but yet I've never had anybody get hurt. It's amazing. So, acknowledging you're going to have to walk around up and down a few stairs maybe. You'll abide by their safety rules. You're not going to intentionally disclose. They let you take pictures though, which is kind of ironic. At least I think. I mean, I've taken pictures and didn't get tackled, so definitely wear closed-toed shoes, long pants, at least short-sleeve shirts. I have seen them send people back to change, and so they like zip back, change, and come back a half hour later. Don't be. They enforce this with no shorts. They reserve the right to not let you in on any of these criteria. I love this one. Tobacco products and aluminum cans. They're not connected, but it's two things that they don't want in their facility. Tobacco is obvious, but aluminum cans, the problem is if that hits one of their glass return lines and then gets put back in the furnace, because there's broken glass return lines where they remelt it, the aluminum can will make this blob of molten aluminum that then feeds aluminum ions into the glass for up to a couple of weeks, and it ruins their production for like a couple of weeks from a single aluminum can. It's happened before. It's crazy. So they don't want aluminum cans or water bottles. You just leave those in your car. So that's what you're signing off on. Any questions on that? Just make sure you sign that before you go. I'll bring that so you don't have to worry about that next week. Just do a sign up, sign in. All right, so let's check the glass and see if it's still too high. I'm going to turn this off quick. Only slightly painful. It's close. What we typically do at this point is it's not quite cool enough to move over to the light table. But what we'll do is just please don't touch any of the fiberglass. That's the only hazard. It didn't happen on my watch. Years ago, there was a student, I think, that got punctured with glass, and you have to like go get it extracted if it gets broke off inside. It's bad. Let's not do that. So I will be up here a little later to crunch off the edge of those so that you can see the color a little better. So just don't touch the crucibles, but you can come up and do some of your measurements if you want. So for diameter, I've got rulers in the box over there. Some people use their calipers. You can call those out, group think it, just try to get a good diameter. You gotta wear your goggles though, or glasses, but safety glasses, because especially a couple of these, hopefully they're not gonna shatter, but don't move them around yet, because they're on a hot spot, and if they move to a cold spot, that can also make them shatter. But I think we still have another 15 minutes before we can examine those. But I'll go ahead and turn on the light table, and you can see what annealed and unannealed glass looks like, along with some plastic parts if you want to see internal stress. So this guy is annealed. You'll notice it has absolutely no signature, where the others are like wild rainbow under this. So go ahead and have at it. Grab your rulers. Yeah, I'll have them lined up here in a few minutes. So you can take a nice. Yeah. Of course. I think you'll be just fine. Clothing isn't a problem. I thought you were going to see it because it would be a movie. There would be an exception. Literally considered work. Yeah, okay. So, yeah.
Just making sure. Okay.
No worries at all. Just don't take it off and throw it in the furnace.
Yeah. Okay, totally. Okay, yeah, perfect.
Yeah, so yeah, thanks for asking. It's a fair question. It was like, like some rooms that have like MRIs. Metal's heat up, so there's rules for that, but I don't think that
We just need a diameter.
Okay.
We'll just hover it over it so we can get more precise when we be later, but.
Like I said, I did already take last records, so you can take those into your lab report. Whatever you'd like.
Oh, it's just like.
This is one which not many. These are ones with a lot. Here's ours.
Okay.
I got a picture. Yeah,
And when you move, okay.
Anything else on here? I think it's just like
Yeah.
estimate, or do I pull this into SolidWorks and get it?
I think we have to do that for all. Well, if you scroll down, it's like a whole big ass table.
It's a little.
I've already snapped a PDF of those. Did you take a picture of all of them? So like you can all be up there calling out colors. Substantiate them, hopefully we'll agree is what they are.
So, flex would be the amount of whatever substance they use. Is that what it is?
Yeah, so you'll just fill out that table to get all those, and then hopefully assess high flux low flux. They actually told the story pretty well. We had some that were kind of average, some that were like pretty flat. Pretty good range, a little better range.
I'd say this one's that dark.
Never mentioned
I got an instant replay up here for some of the batches if you get bored waiting. So it's exciting stuff.
Yeah.
So
they kind of build like
You want like this.
so like put in all the letters. So there.
This one. That one's got like swivels. This one's green with a brown swirl. Yellow. Pink.
that's what we were. Yeah.
You get over here. Or let me take pictures of that. So I'd say for right now, just a picture of it sitting there. And like I said, maybe a picture of that. Hold off.
Yeah, I'll wait before we write down the dagger. Go ahead, put no, you can always try something, put yes, and have green. Well, I'll leave that like ketchup. We've actually made it through but that had to shatter. Well, I had a package in my office. I was in summer, typing up something in my office, and there was this and here's a cabinet. It's a year later. So it's like this statistical tail that makes it like, right, it's never quite gets to zero. But we're already better than most.
Send go down the stairs.
Yeah, once you get on the last table, so usually, but occasionally if I rush it too much, the top of the I have had one split.
I think if it's really close,
Yeah, we started at 8. According to his little sheet. Did we go all the way to Kizzy?
I don't recommend
the R. Did we?
Yeah.
The parents.
Yeah, no,
Sure, Scout's got sandals.
You were trying to cut yourself, but it's just really curious way
Yeah.
Yeah.
Yep.
Oh, right here. You want to the full center? Yeah, this is this is just a few minutes ago.
Nice.
65 grand forward.
I did share. Okay.
Ready to go up there? You want to hold the computer and I can measure.
If you want to see more variety of color, I do have a bunch of other glass samples laid out here.
Yeah. Oh, I see. Like filling in that stuff. Oh.
You see some examples from the past.
Oh wow.
These here are actually from Tuesday, so they kind of went more of a. They were really all about copper. Yeah. Which letter were you guys? Oh. Yeah, it was. So far, it's hanging in there.
Surprisingly enough, I
Oh, you wanted to even thicker?
Yeah, I wanted to.
Well, I think you probably won for the highest viscosity because it was. Right. I turn it upside down and it's like.
It does.
I think there's
powder in there.
Looks like it.
Yeah. So, but eventually.
So what's the plan for this?
Yeah. So I line them up on the bottom, and then I slowly heat up to 550 Celsius, and I hold it there for a couple hours. If you go too long, it'll start to stick just a little bit. The fire brick, you get these like little grit pieces on. So if you do it just right, it doesn't stick at all, and then you turn off the furnace and it slowly cools down. And then at the end, you come over here and look at the light table, you'll see the result. So this is what a high internal stress field looks like. All of them right now are going to look like this. But then this guy has been through a thermal cycle and look, like nothing. Yeah. So this would behave much like annealed regular glass. If I dropped it, it would break. But it's not going to break by itself. This, on the other hand, if I drop it, it's going to bounce. It is hard to break these. Like occasionally I wanted to make chipped glass. I put this in a Ziploc bag and I start banging with a hammer and the hammer like bounces off. It's because it's like already under the surface is under this like internal compression towards the middle. So it's like it's not hitting it. It's like hardened glass. And so you finally have to hit it just right in the middle. The crack is like hard. But It's weird. Tempered glass is weird.
So flux is
This isn't quite the level of tempered glass, but we are quenching it. So we have sort of a rapid cool stress field. But most of these are annealed. Most of these are not annealed. So you'll see clear patterns. Those are from old days. Those also have that clover leaf gold. Yeah, so because of the way I'm pouring in the middle, that's where it's feeding material in. So that's the part that was the hottest and longest, which means it's sort of like the last bit in the middle that's not quite under that much stress. But at the edge, when all that disc starts pulling in, that's loading up spring pressure on that disc towards the center, which is why you get those rainbow bands stacked up around the outside. A lot going on there that is, not cross-polarized, you never see. Yeah. But it's amazing how the science tells the story, and you can really just rationalize everything you see. Yeah, a whole lot. That'd be cool. Get this on an album cover. Like the glass pucks in concert.
Well, you had it half and half.
Oh, okay, okay. So it's kind of like an X-ray. You can see
Dark
inside.
side of the glass.
Yeah,
Dark
right.
side of glass.
The watch look. Sure, we get which one to discuss.
Well, it's disgusting.
I guess. A lot of them are the same.
So you said since we don't have like an A or a baseline, what should we use to?
Right. So I would say that if you, yeah, take them all, just average them on the table, and then just consider A to be average. You know, is it above or below average? Just kind of comment on why.
Yeah, quick question about the percentage.
Great.
So it's not just from the table. We have to figure out how much CO2 is left.
No. The intention here would be to put the final percentage of the metal in the glass. So that's really just transposing from that calculated table. That if you have a mix like copper or chrome copper, you would just say CR and then a percent and then copper and a percent. But for the it's just the percent. Yeah. You know the table I'm talking about. Yeah. So that far right hand side, those are already
What was that?
the CO2.
It's not right.
Right. CO2 has already been factored. That you guys now. Right. And those are just 2 entries. You just kind of put the exact entries in there. That way, you now look at the color, and now you know that that's what that percentage is. With the wild card of
They may not be perfect for this, but zoomed in my phone so that we use the 1/2 scale.
yellow.
Did not replace the same?
No.
One inch.
So that's why we were kind of confused. We had to say, oh, whatever they were. You're saying this was this?
Yeah. And then I'll plug it in.
Oh, okay. That's what class.
It's not perfect, but it works most of the time. You've done that before? Yeah.
What's that?
There's a lot. You can get more advanced and ready to use computers for it if you take a picture not
Yeah,
like
so
grams, we use 200 pictures of different angles of an object. There's a program called Measure that basically does the
iron
same
will
thing.
make this have a tail grip. But why is it tilting yellow?
I think it should be.
So those are kind of similar, but that's not really. No. I would say this is Monday, Wednesday, Friday, but iron can do this. It's like iron can go anywhere from green to brown. You know, like color it amber bottles, that's a lot of savings. If you've ever installed window glass, on how it looks kind of, yeah, that's usually the glass. We'll see that.
Take the picture from
Yeah,
far
it's
away.
there. I should probably change this because this is a little more yellow.
It's like the surface.
Yeah, I
line.
overlooked
I've
that.
got picture of this parallel.
That's very nice.
It's ridiculous.
Yeah.
Weird. Another 45 minutes. No, way longer.
Right.
That is called
So I just do it.
Oh no, I can't.
Like Monday,
Okay.
Tuesday.
So that was from copper. This one. So iron manganese. What raw premium? Oh, I guess that is kind of yellow. But when I hold it right next to it, it looks more similar than the other ones. It really is.
Yeah,
you know what if
Kind of
it's
similar.
well, actually, this one, I got.
I'll have to update that predictor so it's
I
not
got
quite so like.
like a 17.3.
Did everybody have a chance to sign the Cardinal Glass form? Make sure you do. Don't hunt you down next week. So it's up here. It was
oh
Yeah, right there.
and we might be cool enough to move.
Which I think he said that what he does
We are.
is the harder, the harder questions it is, they're like worth less points. Yeah.
Oh.
Or something like that. So I must have got one like the one I got wrong is probably the first one.
I got like
Oh, yeah.
I didn't, at the time I didn't.
Week one, I got 100%. This one we got 17.
yeah.
This week, I guess I didn't know what it was.
Yes. That's my hand.
Oh, never mind, there it is.
So I got. Yeah, last week.
I kind of like this week's.
This quiz. So the cool thing about the quiz, you see early last and how weak this is actually really get a grasp on. It's the same process for everything.
Name, but the chapter 4 so far, I actually understand.
It's really not bad.
I like it more than the
Some of the stuff is very. There's easier ways to see 63.2. Like,
I
just like think about the way it rotates, like this, I plus K or whatever. It's gonna be J, and then you just draw from I to K.
The smaller the diameter,
yeah.
the larger.
It's just gonna be negative. It's all smart.
This next one, the one, right? Yeah.
No.
Oh yeah, you just say you can.
I looked at it.
I also work for questions how they only show third credit.
Yeah.
So
Yep. You don't even know what your grades are. Well, no way.
Yeah, that must be the next one.
Some people you see like grades, I'm some people
0, 2, 3.
Wait,
Wait, you can see. Wait, where are you looking?
Click range by assignment group.
A should maybe be the medium of the copper.
Yeah, I think that.
Because then it would make it like
when
yeah,
I
that's
did
the
it,
copper.
change
Copper,
years
so
ago,
it's
it
the
was
copper.
assigning batches.
Yeah.
Give you the ranges and be like, do you think in these ranges are glass? It's up to you.
Oh.
What you want to be. So I find that if you just gave everybody all the ingredients, these guys, we would probably have some batches that wouldn't make glass. But by the ranges, you get the freedom, still makes glass. I think it works well.
feel like that would be better for consistent going. 1.4. But I'm like doing.
Oh, it's good. These are all.
So like this one kind of like 3 out of 9. Somebody got
Oh yeah, it's a little off.
I don't get that.
Well, actually,
So this one kind of like I got a 2 out of 6.
It's really bad.
Okay.
I got a 2 out of 5. So a 2 out of 6 and a 2 out of 5 is a 2.
You just said like that. Oh,
Yeah.
yeah.
I go through.
I was like, I thought you meant like our actual piece of glass. I was like, yeah, go ahead.
Right.
And then they're very well estimated.
Oh, God. Because I don't think that's going to be hard to change it to a one-on-one. The weight. Like, what's the weight?
What's the weight of those 5?
Right. But then yeah. Once you get all your observations and measurements done, then yeah, it's good to go. It's got sign the form there. That's look at everything. Oh, sure. Yeah, it's on the white table. Yeah, it doesn't. It's not that high anymore. I still recommend safety glasses because they're unpredictable, but it'll be safe to, much safer, I guess, it'll be 2 weeks after. Remember, yeah, you can go ahead and touch it, check out the traditional 0.08. And definitely take a picture with the cross polarizers and see how that's going to change. Yeah. And I know too. I wonder if it's just better in the center.
Unless it's like
It's not bad for one of these days I need to go back and wipe the board.
All of us when the CO don't lecture videos or whatever.
Oh yeah.
C other one CO. We'll go back to that.
Some of them did. Give you the hints on the coloring problems and not the really hard shit.
You told me in the orange, that would be brightest part.
Ours is way back.
You could also just go look at the crucibles.
Yeah, no, that's fine. I'm just gonna kind of add. Yeah. Oh, for sure.
Is it the percentage of their amounts?
Oh no, we don't.
Yeah, that's
Oh, I see. Looks way different. It's like a these up so we get a nicer picture here.
Composition is just
We get
just the grid in that.
which Yeah.
Yeah, that's the actual
Shows
corner.
you, I guess if you don't do the other one.
Yeah, hold two together and turn them, so you'll hear it black. I love these things. You still see through it under
Yeah.
Or, he definitely did not have a diet. That's what I said. We might want to go back and like watch it. Because the time is fascinating. No, and ours was definitely not the highest. I would say here.
Maybe it's just the one across that sucks, but I have never actually put with the bread.
Trying to stabilize that lip so it's
I'm
not
gonna like highlight
quite so
top.
sharp.
Like I can go back and watch the videos and then.
So those are gonna get annealed, and then after they're stabilized, then we're gonna see.
Yeah.
At the moment, they're really unpredictable, so I think that after they've been thermocycled, hopefully they'll all anneal properly.
Well, I just thought I heard someone say they're taking theirs. So I was like,
Yeah, you gotta wait another week, and then they'll be safe after annealed. Or oh, the iron somehow dominated it and didn't tilt the purple. Yeah, so you end up with yellow.
and we even tried like the minimum amount of iron and the maximum thing.
Really?
Extreme.
That's hot.
I think like the sand we use.
Well, that's actually fairly pure sand, so I'm not sure why that wouldn't have expressed more, unless for some reason iron just dominates it.
Yeah, ours ended up looking like the other two iron based ones.
Yeah. I've seen this kind of thing happen before, where you're expecting a color to show up and then it just doesn't. And you're like,
We were hoping we wanted this effect.
oh,
Okay.
yeah. I guess we probably have to do multiple experiments to figure out why did it look different. So.
Okay. Well, I guess it helps
Watch the one couple
Where's the probably not, because at this point I think it's good.
Under the hood, where the engine
But-
is. You should check it.
All your money right now.
Oh, I think we did. I love it. Oh, okay, gotcha. Yeah, I was.
It starts great, but sounds
Okay, yeah, no
perfectly
problem.
fine. Just
Yep, see you later.
get that. It goes on to the bottom of the bell.
I don't know. Did you send it to me?
So yeah, I got your message. Now, would you probably prefer them to be completely vacated, or would it matter if there was something off the side, or? We'll definitely get 6. Probably, I mean, 2 and 3 would be pretty easy. Okay. 4, 6. I got I guess 6 and 7 and 8, and then probably 9 and 10. You probably don't find it asymmetric and not yeah. So we'll definitely have 6.
Yeah, I was
very
gonna say.
obvious.
How are you gonna?
Some have equipment like 1 and the ones with the furnaces are 4.
That
But if you only need 6, that would be okay.
I have a question.
Oh, yeah. So they're kind of single use. So they just stack up. You can see a million of them here. Platinum or nickel crucibles can be reused because you can bang the glass and all falls out. Okay. But these, when you buy in bulk, are a couple bucks a piece. And so they're basically, they are reusable.
Wait,
but
so did you?
only be reusable for a similar batch coat. So we often just start fresh and they stack up until I figure out what they want to do with them.
It's a fine coincidence.
So, it's surplus, right? But my problem with that is people are probably going to try to drink coffee out of it and then be drinking shards of glass. Bad idea. So, so for the most part, they're a consumable.
I think I can now finish this off.
Planning on it.
So I think I'll-
Yeah. What color were yours?
We've had a lot of like half days.
This one.
Do you get
What's
part
so
of the line
iron
on
chrome?
all reconvene tomorrow?
Was it just a little bit of chrome?
It was, yeah.
Yeah, I would have expected it to be more.
We got kernel
Chrome
glass.
is such a powerful color. It always tilts to dark green. But yeah, that's just more of a kind of a
I was gonna.
maybe.
I
Yeah,
don't know what I
that's
was
a more
doing.
brownish spectrum. Some other guys were saying their manganese didn't need
Could try it.
iron and mason.
Is carbon glass?
It's still
Other
under.
than north, yeah.
And we're trying certain like combinations every year
I've
that,
never been there, that's just what it looks like.
in theory, that exact combination can be a never good drug.
Yeah.
So
Technically perfect,
I
but not
kind
a
of try to predict, but sometimes my predictions are a little off.
You can see kind of the rings on all the rest of
Yep.
ours is just.
If you get the right angle of polarization, you can make it similar. You still have rainbow bands with the more of the turbulent pouring zone in the middle. But most of the stress located around the outside pulling in. Yeah, yours does look a little bit. Yeah. Oh, right. There's little like, it's almost like little fringes on either side of the bubble where you can see that the stress field is affected by that bubble, and it's actually concentrating stress left and right. So that's a weak point. Yeah, good eye on that. Have to get like micro polarized analysis. That'd be really neat.
See, thank you.
Yeah.
Possible to make like a polarized coating for glass, so you could still see when everything takes the same shape.
So you're saying actually put a coating so that the bottom layer, top layer, so the dishes look like this all the time. I'm sure the answer is yes, but imagine if we took this kind of like the films they use to tint glass, you know, those aftermarket tinting packages. You could put a film on it that would work. A coating like a paintbrush type coating, that would be challenging because you need to have a defined orientation. But if it was an adhered film, an adhered thin film, yeah, you could laminate that top bottom with that film, and then it would look like this all the time. Maybe I should get a roll of that. But after it's annealed, all that that's the story of glass in 3 hours, 2.5 hours.
Is our reporter that we did do this next Thursday when we go to Party Glass or the week after?
So I've done it both ways. I think I was probably thinking I think it's below next week to keep things rolling instead of
Because I looked again this and it says due the 10th, but I just wanted to check, which is the week after Party Glass. Oh wait, the week of Party Glass, which is the 10th.
Is that right?
Next week would be the time.
Okay. Yeah. Honestly, I could go either way, but I guess it's already in there. The only thing that could be added would be the before and after kneeling pictures. So,
That's a really
yeah. This I think is neodymium. I think. I have to look up that number, but there's a few rare earth colors that we've tried that are really vibrant. There's a certain pink. I'm sure I see it up here, but I think that's neodymium. Glass blower glass is precedent. Isn't that green glass? There's a certain glass blower glass you wear that prevents the sodium D line yellow from getting through, and that way you get less eye fatigue. Because those guys are like staring at a torch all day and burning their eyes out with bright yellow light. So, yes. See you later.
So I was watching one of the YouTube videos.
Yeah.
And so you have it poured on here. And how long till you pull them off? And
So that timing, oh, you mean after it's poured to
yeah,
go
after
over
it's
here?
poured, yeah.
So that's probably around 45 minutes. And so I've been showing the same sequence for a long time. That we show that Dale Chihuly video, art glass. We then show glass bottle making.
Yeah.
Talk a little bit about that. I then often have cardinal glass filter. And so I give them some explanation of that. By that time, it's cool enough that it's not like hazardous.
Okay.
They're not going to catch themselves on fire, but they might burn themselves a little bit. And so I let them move in at that point and start doing their caliper measurements and that. But it's still hot enough that when you touch it, it's like, no, I don't want to keep my hand there very long. But you could do this and not be terrified. It won't hurt. So then after they're all cycled through doing those measurements, it's then usually the point where they're just warm. You can move them over to the light table and do a little more analysis, handling of it. And then once all that's done, I load them back in, and at some point in the next week or so, up to 550, hold for an hour or two, and then kill the power on the furnace and just let it free fall slowly back down to room temperature.
Okay.
And then all the stress just disappears. We have pretty good track records. None of these shatter. So I've kind of refined ingredients to try to encourage stability in the batches.
Okay.
Aluminum tightens it up, often makes it shatter. Potassium isn't as good of a flux, and it makes these tight discs that then they shatter. Lithium destroys my furnaces because it's so small it evaporates and fluxes the wall of my furnace. And so I have not used lithium on this one at all yet. But if you look at the top, you can see that she's sagging. And so over time, small flux like lithium, it's really potent. At least I'm assuming that's part of what I'm seeing. But we discuss those, and I've got pictures of them in the lab, because the more potent that positive charge is, the more effective it is at disrupting polar covalent silicon oxygen bonds and infiltrating that through a process called fluxing of the glass. And even though they're all just alkali cations, lithium at the same concentration is more potent than sodium, which is more potent than potassium at the same pouring temperature. And so you could get the same properties if you had lithium the cooler, sodium, and then potassium the hotter. But since we're wanting to compare them all at the same temperature, you end up with a lower lithium viscosity at 1200 or 1150, and then medium and then a high viscosity potassium, because each glass has its own characteristic softening range, where it gets thinner the hotter it gets.
It's almost like time, temperature, superposition in polymers, except with fine. Yes.
There would be some logical tie-ins, the way they overlap those curves and such. And so this is sort of the viscosity, the thermal viscosity curve, what they call the viscous range of the glass, shifts depending on chemical composition. So if this is our axis where it's hotter getting this way, leaded glass is like way over here. So then you have lithium flux and sodium flux and potassium flux, where viscosity is getting higher. I can see that at a particular intersection point, that's showing where we've got low viscosity glass and high viscosity glass at a constant 1200 degree core. So some of this is in the notes ahead of time. And I don't want crazy obsessed with making glass veneers and that type of thing. But it's nice to see the predictability of the trend. And we had a nice set today that we had some higher and lower flux ratios. So we had some that were big, and we had a couple that were pretty small. So the data's there. It show. I could do more with that. Like I could actually try to get a plot of viscoelastic ranges and make certain assumptions, because we do lots of qualitative assessment. But I don't know. I'd have to find a model and see if it's worth doing that. But so it's not quite as rigorous as PCAM by any stretch. I'm trying to make this more experiential material science, where you can really see the connection of microstructure and macrostructure properties. But it's more involved than, say, a Chem 135 lab, but way less involved than PCAM lab.
And some of the samples in the video cracked.
Yeah.
Is there any like warning signs you get?
Yeah.
Okay.
So whenever you pour and it just looks like it's standing up tall and quite tight, those often crack, irregular shapes. If it flattens out to a disc and when you're torching it, it still seems to relax out, you're usually fine. But if you have large bubbles or unmelted batch, if you see chunks of like calcium carbonate, those almost always explode. So for some reason, if there's unmelted batch, they mitigate that by doing some mortar and pestle work. They're not out right now, but they're in that mid-lower cabinet on that first bench. And so I've been on top of that more, getting them to grind up anytime when they're measuring out their stuff. If there's clumps, some of those clumps, they can't get properly fluxed because it starts on the outside, but can't make it all the way through with whatever time was given. And so unmelted batch makes these instabilities. But then there's some that just explode.
Okay.
So if I see one that I'm reasonably suspicious is going to explode, I do cover it just to have a little more containment. It often breaks the beaker, but at least it doesn't just throw glass all over the place. I've never had injury. I have had them go off in my hand before, and it doesn't really cut you. It just like kind of feels like tap your knuckle with a hammer. It's weird. So it kind of hurts, not that bad. But the worst case scenario could be glass in the eye. And so I always want them to have at least safety glass. These aren't splash hazards, but at least safety glasses. Just because it's really unpredictable. Covering weird batches just makes it a little bit ahead of it. If you do see a weird looking batch, you have about 15 to 20 minutes typically before the first likely time for cracking occurs. You just kind of have to be ready for a little bit of unpredictability. Is this making sense?
Yeah. And then The other day when I was here listening to the pour, or watching the pours, I heard cracking. Like,
Yeah.
Is that the glass cooling or is it the crucible?
So if you look, now we have a completely, speckle crack pattern.
Yeah.
Every one of those little tink, 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 tink that you heard was a new one of those cracks formed.
Okay.
So that's due to differential shrink. The glass is shrinking at a different rate than the crucible, but as the glass then hardens up, it now can no longer give like it could when it was hot. And so now, as it's loading up that thin layer, it doesn't have the shape it can pull against and stabilize shape-wise because it's a surface film like that. And so that's when you get all those little cracks and crazies. And so at the beginning, you can literally look at the crucible and you'll hear it, and there'll be this like immediate line, that shows up in the glass. But these are now obviously mostly stabilized. So, yeah.
Seems like you're good at making glass. You make new ones for sunglasses.
Oh yeah.
Yeah. They got to be polarized too.
Well, yeah, polarized fishing glasses, or like driving
Yeah.
glasses. They do this exact same.
Yeah, I know. That's why.
Yeah, it's pretty sweet.
They're sweet. Yeah. You can see like into water and stuff.
Right, I love those.
Yeah.
They're awesome. But yeah, that's the process called crazing. Different than crazing in the polymer world, but crazing, that's more of a carryover from the ceramics glazing. That's what they call that crazing. Just like fluxing is also used for fluxing for joining metals, right? You're fluxing a copper tube so that you can apply a solder. Kind of the same idea. It's a processing aid or a melt aid. In that case, you're trying to avoid oxidation. In this case, you're trying to encourage melting. Sometimes these terms are interchangeable in different settings.
I have more questions.
Yeah, sure, and I'm always happy to be around whenever needed and help out whenever needed, and especially if it's your first time going through some of this stuff. Like, for instance, the tin smelting lab. I kind of have these, from all the Pecan stuff. Sometimes it's sort of a homebrew type approach. I've got this little crucible in with some fire thermal blanket around and some ceramic wool capitulator, and it makes it like a little blast furnace. And I actually do get to do smelting with charcoal of tin oxide, and it works great. You get this little metallic piece. You can then calculate yield, and you compare that with electrolysis and with sacrificial metal like zinc. We do as a replacement with tin chloride and zinc chloride. So we kind of use that to illustrate all three of the approaches for smelting that are used commercially. But there's a few pieces of that process that are kind of weird because I'm using this air. See you later. I'm using this air-forced meeker burner over a tray of sand because occasionally the crucibles crack. And so there's a kind of a timing piece. So I usually man the that part and kind of help because I don't want students. I don't want to risk people getting burned, and so that's why I try to do more of the danger work up here. And I'm still a little leery of that. I've thought about making a few more of those and having the students do them, but if you got something out of sync, you could probably burn yourself or catch your clothes on fire. So, but I might be making it sound worse than it is, but it's been working great. But it's a little bit of a strange process. So. But that's after cardinal glass. So.
Well, thanks for answering my question.
Yeah, you're welcome. And so you have done quite a bit of polymer work, right?
So in grad school, we worked a lot with glasses, but it was small molecule glasses. But we ended up, of course, having a lot of carryover with polymer stuff.
Yeah. Okay, so then you were doing molecular glass,
Yeah,
not inorganic glass.
not inorganic. No.
So those are like 200-300 degree transitions.
Let's see, some of the stuff was you get a glass transition in about 50 slightly greasy.
Oh, that low.
Yeah. Maybe as high as maybe 60 something.
So then that would be much more like polymer glass,
Yes.
but you're doing it with small molecule.
Yes.
I see.
So,
Because there are some other, I guess those are still inorganic glasses. There are some interesting substances that would have this type of melt behavior, but way further down. But those probably wouldn't be considered molecular. So what were the molecule types?
usually they had a benzene ring or fused benzene rings in it. So the two big ones was there was a center benzene rings with fused benzene rings sort of hanging off of them,
Okay.
different substitutions. And then the other one was a benzene ring with there was a carboxylic acid hanging off one side, and something else hanging off the other side.
And these weren't like liquid crystal type things. These just were like stackable.
Yeah, so if you heat them up and you cool them down quickly enough, they'll just completely turn into an amorphous solid. So we were doing vapor deposition with them, and what we found is that when you vapor deposit them, they would sort of stack on top of each other instead of just the random orientation.
This sounds pretty cool. All right. Well, I guess we'll just keep talking through, and I guess hopefully you're interested in material science and not feeling like you're getting pulled in a strange direction here. But it's definitely a different field than a lot of the labs we got here.
I looked through the labs, and I think I'll be fine. Although this one with all the heat, it's got me a little bit nervous. But
Yeah. I guess because I've done it a lot, I'm spotting the students as well because I've got them working with the torch and the door, and so you have to, like, in your mind be thinking about demarcation from the hots and sharps, you know. And so I'm doing my best to keep everybody safe in that process, but I think that, you know, the best thing to do is to just kind of get a feel for it and keep your movement slow and repetitive. But you know, when I'm first pulling the crucibles, now obviously I can get involved in the firing process and such. It's kind of a slow approach because, you know, it's all hot, you don't want to tip it over. And then once you get it locked in, you're actually squeezing a bit, so you got that pretty well locked in at that point. You've got these goofy gloves on at that time too. But then it's a matter of just kind of keeping it stationary and sort of spotting how big you think that growing disc is going to be, because you don't want to run it into the next one or off the edge. The students doing the fire polishing, so then it's not necessarily time, you're mostly looking at visual cues. Once you see that stream has now become so sluggish that you're not getting much anymore, then you try not to transpose the strain, but you stretch it, and then you kind of pinch it, you kind of relap it on the bottom, and then if the student's heating right, the hot spot then just pinches free, and you can sort of move away, which you probably saw that over and over again. But that process, just try to prevent the fiberglass that then is, besides the heat, that's the next hazard, is fiberglass.
once it's mostly emptied out, do you wait a minute to put it on this, or just kind of?
Right, so I usually want to wait until it's no longer glowing.
Okay.
And so it rests here until we're kind of down on the glow, because if you put it directly on this mat, it does start kind of smoking a little bit, it makes an unusual smell. But once you've got like the next crucible, then, and especially verse 3, the first one, that kind of give it a few minutes to kind of get down below the glowing point before it gets pulled out here, just to get it out of the way. And then as you saw, just kind of dress the surface, try to get all the waste I can toss, and then I line them up. So over the next couple of weeks, we're going to swing by and see the full set of colors that are made that year. So that's the glass story. Make if you think of something creative to do with crucibles, let me know. Well, right, they targeted black, which was an experimental batch. Is it correct, or? So I do see hairline cracks, but it's way, way less obvious.